Went on and gave you guys 11 lectures so far. This is going to be the 12th one. And you don't have quiz, you don't have problem sets. All you got to do is term project. So I feel more duty to help you put it back together as a whole. And I thought we'll start with the class itself. So we have 3370, which you just took. And the fall corresponding one is 3372. And for this semester here, we had essentially two modules. One was really on forming and processing. And the other one, the way the curriculum was written down, said use. We also called it life assessment. But we did go into more than just the life assessment methods. We talk about fracture a lot. We spent time on fatigue and creep and kind of the things that can happen in service. The fall class is more emphasized in material selection. And at least last fall, it was also a lot about, I'll call it design standards and how to essentially bring everything back as get us closer to a product as opposed to a shape. Like this semester we really talked about stamping, forming a shape. But when you talk about standard, you talk about API, how they tell you how to design the whole system. Same does ASME. Same does AWS, for example. We did talk a little bit about standards like ASTM standards. We talked about AWS standards, but mostly for some of the technical information that was in it. So this module that Professor Eager has put together last fall is really giving you a better flavor of when you go out there, the kind of things you may be using, as opposed to arriving to your own rules on how to design things. Some of them are almost written into law. Some others are really just guidelines. So there's a whole range. The aerospace tends to be more formal rules. And when you move towards automotive, for example, it's very general. They tell you where to put the lights always and how many lights you need. But when it comes to the designing and determining the strength of the frame, there's a lot of wiggle room on how to do it and how to test it after the fact. Okay, so with respect to use here, today we'll go back to, I essentially put aside all the notes I had and I started thinking, okay, so what exactly did we do? So we talked about different method to use to predict how the materials, the metals, the plastic will behave. When I say damage tolerant here, I'm referring mostly to fracture mechanics. We did talk about the R curve. We did mention about J integral. There was a lot there that had to do with the fracture, essentially. We talked about fatigue life. And we also talked about creep. For creep, you can essentially use the same two techniques to do the same thing. And then I gave you relatively specific examples for metals, where the grains, for example, play a role, the heat treatment play a role. We talked about polymer and how you stretch the chains to influence the behavior. And we also talked about joining these bolts that we had this discussion about whether you want to preload them or not. And the welds, also the fact that welds reduce your strength by a significant amount, especially if you have repeated loading. Okay, so fracture mechanic, and that ties back to actually the last class. Professor Eager said at the tip of the crack you have a plane strain condition, which is essentially means that you can't have flow through the thickness. So the thickness is the z-axis here. And therefore, you're building up that triaxial loading. And the triaxiality makes your flow stress goes up. Because The flow stress is, the difference between the minimum stress and the maximum stress. If you raise the minimum, now you can be there without yielding at higher load. And that reduces the plastic zone size. So that's an example here of plane strain with a smaller plastic zone size, because you have a sigma. If we go back to those principal stressors, so sigma 1, sigma 2, sigma 3, in this matrix form we had, when you're in plane stress, you have one here that's 0. So I'm going to call it plane stress. And that is what makes this condition yield you a much bigger plastic zone than if you have stresses that are in tension in all three principal direction. And that's what we're looking on the screen. So the top is, we have a 0, and the bottom is, we kind of have, maybe for, I would say for plane strain, we may have the sigma 2 and 3 being similar. So now it's only the difference between the pulling direction and one of those two that's the driving force for having plastic deformation. So it's going to be much harder to do. That's the idea. And that's why your stress level, that's why the sigma 1 is going to go up, and eventually you can snap, you can form a crack, because you yield locally where you have an impurity, either in the plastic or the metal. And we looked at some of those. If you remember the plastic sample, it could be like a micrometer size, but they're there. And when the stress is high enough and you have that tension, you really grow little voids around those impurities, and that's how eventually it snaps. And you can form a cone and cup shape, like on a tensile test. All right, so this is a view through the thickness of that plastic zone, showing that near the edges, you are allowed, like here, you are allowed to reduce the thickness. It's a free surface. So on the free surface, you can't have tension in the thickness direction, and therefore it is not a triaxial state. It's this state right here, plane stress. But as you go towards the center, now the material that's stressed highly around the tip is constrained by this mass, this elastic mass of material that's around it, and that's why it doesn't shrink. The yielding and the, let's do those first. So we talked about fracture toughness, and I introduced that slide saying that K just happens to be a function that gives you a solution to the stress field around the crack. So what we have here is for all three directions in the plane as a function of the angle and the radius. So you have here on the denominator, you have the square root of radius. It tells you what the stress level is. Now, once you, so it's a characteristic, and I think I mentioned to you the same, well, it's called the stress intensity. So it gives you the amount of excitation to the crack, which is load and the size of the remote load and the size of the crack. And then you have geometrical factors to take into account. But it's essentially built into an elastic field equation that we use even though we have plasticity at the crack tip. And one of the reasons for mentioning it to you is a lot of time with plastics, we can't use the equation. See, or even we had an example, just growing a crack by tearing. If you have too much deformation going on, if you can see deformation, it probably means that it's not confined enough that you can neglect all the plasticity aspect for the elastic profile, essentially. So we're solving for an elastic profile, and then we're happy when we're happy with the result of just this simple equation here: stress square root of crack length. And we can use it by running a test. You go to the lab, get a crack a certain length, apply the load, and find out what is the fracture toughness of the material. So when we say fracture toughness, a lot of times we'll talk about K1C. So the C stands for critical as opposed to just K. So if we have K or K1, this just means how much load you're putting on it. So that's the intensity of the stress. Yeah, I think that's what I call it: stress and crack together. And this one is the material property. I would really hope it became clear after we spent the time doing this. But you can always go back. There's complete ignorance, there's forgetting, and then there's completely remembering. As long as you remember something, that there's a tool that you can use sometime. In general, it's enough. Now, using those simple concepts, we talked about fatigue crack growth. So you have your sample, and I can put them essentially. So see, the cracks goes up to here right now. I load this in tension. It's more or less of a laboratory sample on this shape. So say we already have the crack, and then we apply a load, cyclic load. So we have a delta sigma, and we also have our crack length. Well, we'll put it, it depends, but put it A here. So that becomes our delta K, which is the horizontal axis, and I'll put a Y here for geometry. That is essentially the horizontal axis there, except that it's on a log scale. And on the vertical scale, we're really looking at how much distance each time you cycle the crack's going to grow. And we talked about that, saying that it will grow because you blunt and unblunt it, and then through that process there is a certain amount of flow. And that's why sometimes we do see so-called striations on the fracture surface. Not always, but a striation is because you open and close, you open and close. And you're going to go faster if you have a high intensity of closing, a high range. That's why it's a question of range here as opposed to maximum value. So all I'm saying is if I'm having a load here, and I'll put it as a stress sigma, that's going like this, for crack growth, it's not going to result as much than if it's doing like this. Well, it's not the same frequency here, but the per cycle, the fact that you're going down further is crushing back your metal in the plastic zone. So when you do it again, you can get a greater step per cycle. Okay. So that was actually when we talked about loading ratio R, which was the minimum over the maximum. And I mentioned there, the reason it's relevant is when you get one of those crack propagation curve with the Paris regime in the middle, is the curve will be very different depending on this loading ratio, given what we just discussed here about the amplitude as opposed to the maximum value. So it's one of those things to really look for. For metals, normally the frequency doesn't matter as much. For polymer, it can play a role as well. And if you're doing stress cracking, then obviously, or stress fatigue corrosion, then it will matter, you know, what's the loading rate and everything. So it's a little effort if you're going to go and say, I'm going to do this type of analysis, to make sure you have appropriate data. If you want to have a general idea, you don't, if it's a certain strength of steel, you could get a curve for, and then you may want to put a range onto it, because it will vary from one material to the other depending on quality and specific yield property. We talked about strain hardening quite a bit, but Professor Eger also talked about it. So aside for today, you guys are experts, and we're not going through the details. It does relate to the stress strain curve, right? And that's something that came in the last lecture with Professor Eger. He said we had a strain hardening exponent n that you can evaluate from the stress strain curve, and the higher it is, the more the flow stress goes up as you deform the material, and it's good for forming. It's also good for distributing stresses around the crack tip, and we had some images of that. Now, if we move away from this idea that we're pre-cracking and we know the crack length, no, here there's a lot that we need to know. We need to know our loading ratio, we need to know our geometry, crack length, and the material property here, K1C. When I say crack length, it really means something, because a lot of times you hope to make a product that, you know, doesn't have cracks in it. So if you have to make the decision, what's the worst product I'm going to make, it's hard. One way is to use the inspection technique. So when I was working at Bombardier, if we were going to do a liquid penetrant test, for example, on all the aircraft components, we'll go and evaluate what's the biggest flaw that the inspector may miss, and use that as the starting point for the life of the part. But the only way in practice we were able to do it was by redundancy. So we had somebody do the liquid penetrant, and then we had somebody else do any other type of non-destructive eddy current, ultrasonic, any sort of test, especially on welds, and you hope they get in competition. So if somebody finds something and the other doesn't, now the other is like, oh, I really got to work harder next time. I mean, if you really have to be sure there's nothing, then you can't typically rely just on one inspector. Especially when you talk about very large volume, very large surfaces that essentially always have to be good. So if we're not going to go that crazy, having two inspectors with different techniques, you have to soak the thing and take it out, look with the lamp, and it never ends. Quality control can be a significant portion of the manufacturing cost, actually. So if you're not going through there, you say, okay, my application turns out not to be as critical, but I still don't want to look bad. So I want to evaluate my product for strength, and I'll give it a certain safety factor. And one way to do it is to load it. In this plot, this is a stress strain curve at a constant amplitude. Figure out how much time it takes to break. And you can do those tests, you know, on straight bars, but you can also do it on welded assemblies. It's actually a good way to reduce your over design, if you will, because I didn't mention when we're talking about AWS that because it's an approach that you can use with any steel, almost any weldable steel, that there's more safety factor built in than if you're doing it in a very specific condition of geometry, quality of the weld execution and all that. So if you have an assembly, you say, I want it to last forever. That's where we talk about endurance limit. That was actually 10 to the 8. But a lot of times we have the fatigue limit, which is at 10 to the 7, in a case where you don't have a plateau here on that stress strain curve. So I think in general, you don't necessarily have to design for a fatigue limit. It's really if you have more of a vibration application. But a lot of other application, if you're thinking about a car, for example, you're going to go and hit real puddles, hopefully fewer than, you know, a couple 100,000 cycle. I'm just estimating here, but if it's a commercial vehicle that's going to be on the road all the time, now that number goes up. So it's really knowing the expectation of the load and number of cycle is important. And we did talk about the minor rule for when we have multiple load levels. We can just build a table, well, I'm going to have so many at this level, so many at this level, and just use that together with the same type of material data. This is our material data, and then we have to figure out how much consumption of the life we get for a different loading scenario, whether it'll be constant amplitude or not. I mentioned that essentially when you're at high load, you start to crack quickly. And that was the best example of that was that polymer fracture surface that I said right from the middle impurity, and we had probably 12 cracks going all around and spreading. And I essentially said if it was really hard to start a crack, there would be one somehow at a corner that start earlier and just go around the particle, so you would not have the crack propagation line. So it will look, the way we had it, we had the particle like this, and we had the crack propagation line at many locations. If it was a low stress level, and say this is a sharp corner here, it will just start here and will grow. Now these are not crack propagation line, this is the direction of cracking, and just spread around. In this case here, it was just radiating from the particle. This would irradiate from the initiation site. So high load, low load. And if you have an application where you have a few cycles at high load like that, and then you go back to a regular, call it vibration, it's quite possible that you'll fail below the accumulated damage of 1.0 according to the minor rule, because you started cracks that you would otherwise not, or you have to wait much longer at a lower load. So that's one of the really pitfall of the minor rules. The biggest anyway that I'm aware of. The tensile specimen. We talked about it a lot. We talked about the deformation essentially being regular through the whole length of it up to this peak, and that the other half of it corresponds to the formation of the neck, and then we have a local stress that's still higher. So when we make the correction for this curve, we make it locally, we see that it's not a plateau here, it keeps going up. At this point becomes at an elevated slope, and to be able to do the other half, we would need to instrument better the sample here to keep track of the actual area. So if I was taking track of the area across the neck here, I would get the curve to keep going up, essentially. But for our purpose, we can still use the elongation at break as a form of indication as to how much ductility you have, because this neck will continue and maybe become about half the section of the original sample. But if it's very ductile with a lot of hardening, maybe you'll get 60 or 65. So you'll be able to get a few more percentages on your engineering strain here.
Before you change that, anybody see an error in that slide? Look where necking begins. Is that where necking begins? You've got it at the peak, the maximum. You remember the Consider construction? It says it has to be the secant, which is the tangent of the curve. Draw a line from making any sense again before there?
No.
No.
To do the Consider construction, you change one of the axes from engineering to a true.
No, but you can do it either as engineering strain or true strain.
No, but to do the tangent, you already elevate that curve by correcting. Yeah,
Okay.
good.
So that is an error. Okay. A lot of people will say that, but that's the case. It's not at the maximum.
Okay. Oh, that was the propeller boat example we talked about. And we talked about it for different reasons. Because one thing I said is there was a flaw, and that's why it really started in one corner. Even though it was a rotating bending application, it started in one corner and went all the way in. So that was an indication that it took time to start that crack, because no other cracks had the time to do it. So this one turned out to be, a little bit bigger, but still it was part of the time in terms of fatigue was involved into creating the initial flaw. And then we can see that it actually went very far. It went at more than a third through the cross section before the overload. And when last time maybe I showed this one to you, we were not too much into the features of the fracture surface, but now I can show you. You do have here a crack propagation line right here. There's a little crack propagation there. So I say one site, it's actually not 100% true. So it's 3 little cracks, but very close to each other. And these are crack arrest line here. So at one point in time, the crack was doing this elliptical shape here. And we see the very big one near the end. And I think with what we've talked about in the class here, with stress level, in this case it's bending, so they have solutions for figuring out what is the equivalent stress intensity factor, giving the depth of the crack and the load applied through the prop axis. So you can go and either say how strong the material property was, so the ultimate K1C value, or if you know the K1C value, you can back estimate what that stress level was. So that's a little bit part of failure analysis, but it shows you the relationship between that you get. You have a lot of information. If you know how big was your crack before the final failure, you gain a lot of information about the material and the application, depending which side you're trying to evaluate. Now, this was something a bit on the side that we talked about, but it was tying back because these fatigue cracks, they go on a very small scale through the material. And essentially what I did for you is try to emphasize that even for the same yield strength, for example, you could have a different crack propagation resistance depending if your microstructure forces the crack to go up and down. Typically, these bifurcation consume energy, and there are multiple ways to think of it. One that I did not mention yet, but it's really true, is if you have a very steep fracture, when you unload, it's very hard to put everything back together. So if I'm cracking like this, and I have my other fracture surface it's supposed to fit, eventually it may not fit so well, and I'm not going to be closing my crack completely. And this crack, the lack of crack closure, so when the two surfaces hit with each other, increase your resistance to cracking, because now, say that the crack tip is right here. It's like if you putting a wedge so it doesn't unload, and then you have less amplitude at that location. So it's also something that is affecting a lot of the experimental data. For the plastic pipes, it's typically a creep situation, because with relatively high temperature with respect to the melting point. So polyethylene pipes, we talked about that you can have them pressurized for 20 years, but you'll have to lower that allowable stress. So build a thicker wall and work at low pressure. But it doesn't corrode, and it has advantages. And then you have to worry about the environment. So we think of plastics as being resistant to the environment, but I still do have my ski binders. Nobody claimed them. That essentially didn't have any or not enough antioxidant left in the compound to prevent this deterioration because of just weathering the sunlight. So they were good for 10 years, because when they compounded the plastic, they added enough of these antioxidant, and now they consume. So that's it. The other pipe products are the same, and some of them also, you can put additives to make them more resistant to this type of smooth cracking that we're getting here. And I did mention the problem there is the recipes are a lot of times proprietary, so it's hard to know exactly what manufacturer does as opposed to the other. So either you rely on what they're doing. If you do that, normally what you do is try to make sure your application fits into their intent, the application. That's always key. We were looking last week at a project he's working on with a car crusher, and clearly the chemistry of the steel was built for welding. So I said, go ahead and ask them what they suggest for how to weld it. Because if they went through the process of optimizing a very special chemistry to be able to weld, they may also have tested with different types of welding electrodes and processes to figure out what works, if it requires a preheat or not. So it doesn't mean they'll know, but there's nothing wrong with asking. A lot of the polymers, we talk about the chains in general, but a lot of them, they do have this crystal or semi-crystal shape here, and it's this structure that comes into play when you're deforming them. So when you start forming a neck in a plastic sample, if it's a semi-crystalline polymer like this one, it will essentially go from a round spherulite to more of a cord type structure, so a nylon cord structure. That's how you make nylon. So you start, you have to nucleate, you can't really, and then you deform it up until it's organized this way. It's much stronger. So we talked about, Professor Eger mentioned that it's the polymer that get the second hit on here on hardening, but we can literally see for the semi-crystalline polymer, it really has to do with the alignment. So now if you take a nylon cord and you pull it, you're not going to get a second hardening regime. It will snap. So it's not intrinsic to the polymer. It's really because you get the opportunity to first organize the polymer. So this would be the case of polyethylene, polypropylene, nylon, PVC, a lot of heavily used plastic. So if we would put it this way, at least for piping application. That was just to talk about how we go to do a 50-year life based on maybe 6 months of test data. And the idea is to vary the temperature and vary the stress level. But you have to be careful because we see that transition between a certain failure mode that has this slope to another failure mode that has a different slope. And therefore, if we were to just test here and try to extrapolate, we'll be missing the right failure mode. So, and that's something to keep in mind in general with any accelerated testing. If you're trying to look for the effect of a chemical, if you put too much chemical, that now you're dissolving the plastic, for example, that's not really related to what would happen in service. If the situation in service is you do get cracking, then you have to find a way to get a cracking behavior. Otherwise, you can't really extrapolate from your test data. So a lot of times, the way to know, say if there was something in service for an extended period of time and it breaks, you should look at it, because it's not every day that you can have data from 30 years of exposure and compare it with whatever you're able to do in the laboratory. In joining, I think this part we covered in details. I hope I scared you enough that if you're going to put a well and load it cyclically multiple times, that you have to take down your allowable. And there are different ways to do it. The AWS is the simple one and the most scary, because you get down way below 10 KSI, even though your material is definitely a yield above 30. And the reasons for that were the heat affected zone, which is where you heat up right next to the well and cool fast. We talked about residual stresses also. That was just a few lectures ago. The bolts, we spent quite a bit of time talk about the idea, and we built this diagram, the Goodman Diagram, to establish whether you're below, so below this blue straight line here is where we don't predict any failure for a certain amplitude and mean stress combination. And then the other curves, for a large number of cycles, that's the blue one. That's a Goodman analysis. And then everything else above that are more sophisticated analysis that I did take into account fewer loading cycles and a slightly different interpolation. If you remember, the idea there was simply that you can have two conditions. So if this is the mean stress and the alternating stress, if we do a fatigue test with no mean stress, we were getting our number here. That was one value. And then we do a test, a tensile test. We did another extreme. And then I just said we'll draw a line between them. And that's what Goodman did. And I also added that I wouldn't go beyond the yield here. So I limited that curve, if you will, doing that. But from there, you can say this is 10 to the 7 cycles. If, like I'm doing on my plot, I say it's only 10 to the 5 cycle that I'm looking at for fracture stress, then it's going to go up or it's going to go down. So you just vary this point here as you need to. And then you can make it into a curve if you use a second order equation as opposed to a straight line. So it's really the advantage of the straight line, it's a little bit more conservative. It's easier to do, to be more precise than the curved second order equation is apparently more precise, but sometimes not conservative. So it really depends on the specific condition that you're looking at. So I introduced this concept here of Goodman for bolts, because that's where it's used a lot, because we preload the bolts. So instead of loading the bolts, the example I introduced over here, this would be a condition 1. What you do is you preload it to about 80% of the yield, and your amplitude is going to go down by approximately a factor of 7. So this is very rough here, but the idea is you get into the safe zone. And you try to have a margin there, given that, how the things get torqued up and the friction and everything that comes into making a preloaded connection. But that's the reason for, I'll say, caring about it. It's not so much to make sure that bolts don't come loose. It's to reduce the amplitude. All right, so this one was the example that I mentioned first class on damage assessment. It's the front of the aircraft wing that has, on the interior of it, well, so it goes into a closed position in flight, an open position to create more aerodynamic for takeoff and landing. These are the actuator for this is what you hear all the time when you're trying to get off the plane, and it makes all these like, so it's just this system. Well, the original jet, which is what I worked on, makes noise. It's unbelievable. You feel that they should, I don't know, try not to scare us, but so one of the reasons the design was a little bit more complicated here is this big holes is to get some secondary exhaust air to eat up the wings so you don't have ice formation during flight. So the temperature inside that portion of the wing is higher because it's at the front than anywhere else. And therefore, what's in green, the primary structure, it's also the same component as this here. They didn't want to build it out of aluminum. And then for weight, another option was titanium, but it's much more expensive. And then the forming technique or the manufacturing technique really became into play. So the way it works out for a typical original jet or aircraft is the total cost of having an airplane is really broken down into, well, you have your maintenance, you have a lot of different things here that we don't worry about. But if we go to first cost here, and we have the cost for fuel somewhere. Where's the cost for weight? Okay. Weight here essentially is the performance based on weight. So it costs as much fuel to run the aircraft as the whole manufacturing of it. And then it costs about 4 times more fuel than the material cost. So it just gives you some idea that you can be willing to put a little bit extra money in manufacturing if you can reduce your weight. Now, for that specific geometry that I worked on, the idea was, so it looks just about like this. And it has this rib shape. So it's thick on all the edges, but then it gets super thin in between. You have support holes, say right here. Now, when this gets loaded, it's only connected through here, and you have the wind pressure. So it's in a bending condition. That's the main loading. And you'll have a side in tension and a side in compression. And the idea is, if you're doing the design, you may need to make, this is the compression side, you may need to make this one thicker than this one, and it will essentially relate to your overall amount of material you're going to need. So the way I did that specific project, and there are many ways to do it, say, look, I need about the same amount of area for my tension and compression zones, that I'll design them separately and then try to put them together. So for the tension side, you worry about cracking. And that's where I essentially use both the total fatigue curves and also damage tolerant, assuming there was already a flaw in the casting to begin with. And the Paris equation says, is that going to grow to the critical size in 30,000 takeoff and landing cycles. For the compression side, it was a bit more boring for me. It was just a buckling equation. But at the end of the day, you need to take from the very general problem and be able to put numbers in. The numbers were different if it was a machine component of titanium or if it was a casting, for the size of flaw to expect, and also the fatigue properties. It didn't really matter for the buckling equation. And that's really how it processed. I'd say that you don't start from scratch very often. So we ended up making a one-by-one comparison for a specific titanium alloy between a casting and a wrought product that became like very specific on all the details, as opposed to brainstorming as to all the materials we could use. So we did a little brainstorming first, and then we were close enough to say we'd like to move to a casting, but can we do it? And then have to go through all these processes. They did. It was a great cost saving. This is where we started at the beginning, just putting it back just for your benefit, where this specific class, we really did two things. We talked about how to make the material, not so much in assembly, mostly on parts. And then the other half, that was Professor Eger, the other half on the use, I try to give you some basic tools to understand how the materials will evolve in service and what to look for, essentially. So I'm looking to feedback, because definitely it was my first time doing this, but I may do it again. So, any question?
Sometime in April, we will send out the